Okay, so before I go into today's lecture, I was thinking to move the quiz uh, to Monday because then you will get the whole weekend and Friday for solving the homework problems. Let me know what you think. I created a poll in that MS Team. Okay. All right, so let's begin today. Last time we stopped at this point. So independence to random variable are called independent if the joint PMF is the product of marginal PMFs. So let's recall that. Recap. Two discrete random variables. Are called independent. Their joint PMF is the product of their marginal PMFs. If the joint PMF is the product of also two discrete random variables x and y are independent. Y are independent. They are conditional PMF. Is the same as their marginal PMFs. Which means okay. Which means that f of excuse me, x given y f of x given y excuse me, I given j is same as fxi and also f of y given x j given I is same as f of yj. Excuse me. Okay. Anyway, so if you look at a previous lecture, so from chapter 3, when we start talking about independence, where is that? Okay, at some point of time, yes, so I think here it is. So independence, by independence, there was this thing that probability A intersection F, sorry, not this one. It's a different one. Okay, there it is. So probability of E given F was probability E, probability of F given E was probability of F, and probability of A intersection F was probability of E times probability of F. So all of those are equivalent, and if that happens, we call that independent. Similarly here also, in case of random variables, if two random variables are independent, then their joint PMF, which is x equal to y, y equal to z, is probability of x is equal to y times y is equal to z. Or you can write that in terms of conditional thing, which is this one, that x given I, x given y, I given j is same as fxi, and y given x, j given I is same as fyj. Okay, so let's do one example. Okay, so toss a coin 4 times, and let x be the number of heads, x be the number of heads in the first 3 trials, and y be the number of heads in last 3 trials. And you want to find the marginal probability mass functions of x and y. So find the marginal PMFs of x and y. And you also want to determine whether x and y are independent. Also determine whether x and y are independent. Okay, so let's draw a scheme. Okay, so what is happening here? When you toss a coin 4 times, there are 4 slots for outcomes. Okay. Right. And x counts the number of heads in first 3 slots, and y counts the number of heads in last 3 trials. Okay, you want to find the marginal probability mass functions of x and y. So that is very easy. First of all, the marginal PMF of x. Okay. marginal PMF of X is given by F X I, which is probability of getting I many hits in first 3 trials. That we know very well that out of 3 trials, probability of getting I many hits is 3 choose I. 3 choose I. P to the power I. One minus P to the power 3 minus I. Okay, and this is for I between 0 and 1. Sorry, I between 0 and 3. Okay, and by the way, I forgot to mention that when I'm tossing a coin, this coin has probability of getting head is P. So probability of getting a head for this coin is P. Okay, and similarly for the marginal PMF of Y is going to be F Y J. Fy J. This is the similar thing as the previous one, which is going to be 3 choose J. Three choose J. P to the power J. And 1 minus P to the power 3 minus J. And again, this is for J between 0 and 3. Okay. All right. The next part was to determine whether they're independent or not. So to do that, let us calculate these things. Let's say for the joint probability mass function Fxy, and we want to calculate it at say 1 0. Okay, x is equal to 1 and j is equal to 0. Okay, which is simply probability that x is equal to 1 excuse me and y is equal to 0. This can happen only if you see this pattern, which is probability of you first get a head and then all tails. Okay, so in that case, this is the only case where you have one head in first 3 trials and 0 heads in last 3 trials. Okay, and if you think of other cases, you cannot have this thing, because for example, if you have a head in the second place, then that would also count to the last 3 trials, which will give you y is equal to 1 as well. So this is the only case where you have x is equal to 1 and y is equal to 0. Product of that is first one is a head, which is p, and all last 3 ones are tails, and that's going to be 1 minus p whole cube. Okay, and you can check that this is not equal to fx1 and fy0. fx1 and fy0, which means that x and y are not independent. So x and y are not independent. Essentially, the point is that if you want these two random variables to be independent, this product rule that fxy ij equal to fx ifyj must hold for all ij. If it fails for one ij, it is not independent. So that's what is happening here. It fails for I is equal to 1 and j equal to 0. fx10 is not equal to fx1 and fy0. So therefore, x and y are not independent. Okay, so sorry, my drawing pad is creating some trouble today. Does anyone have any question up to now? Okay, let's see. Okay, so the next that we would like to move to is the continuous case, which is joint distribution for continuous random variables. Okay. All right. So I'll start with an example. Consider the following rectangle. Draw this rectangle. Okay, so this is my x-axis, and this is my y-axis. And suppose there is a rectangle which is like this. Okay, so this is the line x is equal to a. The left hand side is x is equal to a. The right vertical line is x is equal to b. And this first horizontal line is, let's say, y is equal to c. And the last one, let's say y is equal to d. Okay. Now what do we draw? What do we do? We pick a point uniformly at random from this rectangle. Okay. point at random from this rectangle, and let xy be the let xy be the location of that chosen point. Now you notice that this xy is a two-dimensional random variable. Okay. Now, first of all, we need to figure out what is the joint probability density function of this x and y. Okay. The joint probability density function of the joint PDF of x and y. How to figure this out? So since the point xy was chosen uniformly at random, the joint PDF will be 1 over the total area of the rectangle. So in other words, let me write this fxy. So this joint PDF, which is fxy, xy is going to be 1 over the total area, which is b minus a times d minus c. Okay, and this is valid for a less than equal to x less than equal to b, and c less than equal to y, less than equal to d. Okay, now if you are wondering why this is the case, why it is 1 over the total area, let's compare this problem with the first problem that we did in continuous random variable, which was this uniformly chosen point from a interval. Okay, so like this one. All right. So you choose a point uniformly at random from this interval, and the probability density function was 1 over the total length of the interval, which is 1 over 2. So that was the one-dimensional case. That's why you get 1 over the total length. But in multi-dimension, you get the 1 over the total area or 1 over the total volume. It is if it is chosen uniformly at random. Um, So for example, okay, other thing is the marginals. Okay, so let me do the marginals. Marginal PDFs of X and Y are given by. So to do the marginal probability density function, what you do, you integrate out the other random variable, right? So fxx is going to be, oh my god. Okay, so this is integration of the joint PDF fxy, but over the other variable, which is y. Hello? Okay, so if you integrate this joint PDF with respect to dy, you get integration excuse me. Integration of this 1 over b minus a times d minus c. So b minus a times d minus c. Dy, and this integration from on the range of y, which is c to d, and this will simply become 1 over 1 over b minus a. Okay, and this is valid for a between sorry, x is in a to b. Okay, and similarly the other one, if y, which is the marginal PDF of y, will be 1 over d minus c, and that is for y between c and d. Okay. So one thing I'd like to mention here is that the domain of marginal PDFs of X is obtained by taking the projection of the domain of the joint variable x and y onto x-axis, and similarly for y. Okay, so what I mean here is if you look at this, if you look at the above calculations, so I wrote that the domain of x is from A to B, domain of y is from C to D. This is essentially obtained by looking at this picture. So this is the joint PDF picture, and if you take the projection or shadow of this picture onto x-axis, the shadow will be confined in x is equal to A and x is equal to B. And similarly, if you take the projection of this picture onto y-axis, the shadow will be from y is equal to C to y is equal to D. So this is how you figure out the domain of the marginal PDFs, and this is for any joint distributions. Okay. And by the way, so in the above example, x and y are independent. Okay. In the above example, check. In the above example, the joint PDF is the product of marginal PDFs. Joint PDF of xy, joint PDF of xy, product of marginal PDFs of x and marginal PDF of y. Therefore, x and y are independent. X and y are independent. All right. Now, next, I would like to talk about finding probability of a particular region. Of a particular region. Suppose, okay, so let's look at a particular case of the previous example. Okay.
Sir, excuse me.
Hello.
Could you please tell me that if a point will be on the diagonal of the rectangular region?
Say that again. I cannot hear you. Say that loudly.
Sir, I am telling that suppose we are taking the point on the diagonal of the rectangular region. Sir, on the any diagonal of the rectangular region. So, sir, how we will do that?
How do you what?
No, sir. I am telling that suppose the probability of getting that point is the joint PDF of x and y if the point is lying on the diagonal of the rectangular region.
See, I think there's a basic confusion here. When you are talking about probability density function, this density function, okay, so this density function doesn't represent the probability of getting point at that location. It is a density function, right? So, do you recall the difference between continuous and discrete random variable? In discrete random variable, so when you have this thing, so this fx10 in discrete random variable is probability that x is equal to 1, y is equal to 0. Okay, but in continuous random variable, when I write so somewhere maybe like okay, so any of these example, if x is continuous here, right? So fx x lambda e to the power negative lambda x. So if I take x is equal to 1, then you get lambda e to the power negative lambda. That is not the probability of x is equal to 1. That is the likelihood of x is equal to 1. Because in continuous random variable, probability of getting any particular value is actually 0. Okay. So no matter whether it is in diagonal or whatever, so I think your concern is that if you take x and y in the diagonal, this b minus a becomes 0 or something, I don't know. And so this fxy at xy is not the probability, right? So this is this thing. So my pen is not supporting me today. This thing is not the probability of x is equal to x and y is equal to y. X is uppercase x is equal to little x, and uppercase y is equal to little y. So this is, so it is a continuous distribution, and this is not the probability density function is not same as the actual probability at that point. And I probably have not answered your question. Can you ask your question once more time?
I am telling that the probability density function, can we get something that on the diagonal of that rectangular area?
Yeah, so what is the problem? Like if you take, so diagonal, right? Something like this. If you take diagonal of the rectangular area, and what you were asking?
Probability density function. The
Probability
joint
density
probability
function
density.
along the diagonal.
Yeah.
So it is same, right? So whatever it is written here, it is same. This probability density function is valid for all the values of x, which is from a to b, and for all the values of y, which is from c to d, which includes the whole rectangle, including the diagonal. I don't understand what the problem is. Is there going to be any special problem if I take x and y in the diagonal? Hello? Hello? Okay, so maybe I should do the next example, and which will actually talk about the probability of a particular region. Okay, and maybe it should be more clear after that. So, probability of a particular region. Okay, let us look at the following particular case of the above example. So in the above example, let us look at this picture here. So this is x, that is y, and suppose it is let's say, what do I do here? So x is between 2 and 3 maybe, or maybe 1 and 2. Okay, so x is between 1 and 2, and y is between, let's say, 0 and 3. Okay, so y is in between, so this is 3. Y is in between 0 and 3. Okay, in this case the joint PDF is going to be fxy uppercase xy. So by the way, you should notice that whenever I'm writing a random variable, I always write those in the uppercase, and any particular values, say little x and y, are written in the lowercase. This is a common convention in probability theory. This will be given by 1 over the total area, which is So this is length is 1 in the horizontal direction and length is 2 in the vertical direction. Sorry, length is 3 in the vertical direction. So this is going to be 3 times 1, which is 3. So this is going to be 1 over 3. And this PDF is valid when x is between 1 and 2. 1 less than equal to x less than equal to 2 and for y between 0 and 3. Okay. Now what I want to do, I want to find the probability that x plus y x plus y say less than 2. Okay, so x plus y less than 2. Okay, how do we find this? X plus y less than 2. So let us draw a line which is x plus y is equal to 2. That line is going to look like something like this. Okay, and x plus y less than 2 is going to be this portion, which is inside this shape. Okay, actually x plus y less than 2 also include all those stuff, everything, but we do not include those because those are not inside our probability domain, so we do not look into those parts. You only look into this part, that x plus y less than 2, which is this, and we will be doing integration of this PDF on that region. Okay, so this probability is going to be double integration of the joint PDF joint PDF f x y little x y dx dy, or you can do dy dx, whatever. Excuse me. Okay. So this is going to be integration less than, okay, so let me write this down, x plus y less than 2. All right. So this is going to be equal to integration Okay, fxy xy is 1/3, and then dy dx. The limit of y, if you do this double integration, limit of y is going to be for any given x. Okay, so for any given x, the limit is y from 0 to this line. So this line is y is equal to 2 minus x. Okay, so this line is y is equal to 2 minus x. So limit of y is going to be 0 to 2 minus x. And bounds of x are from 1 to 2. So let me write that down, 1 to 2. Okay, if you evaluate this integration, this is going to be 1/3 excuse me. Okay, let me do it by my pen and paper, and I will just write down the answer here. So this integration is 1 to 2, 2 minus x dx. 1/3 is outside, so this is going to be 1/3 2x minus x square over 2, and we put the bounds from 1 to 2, which is 1/3 4 minus 2 minus 2 minus 1/2, which is going to be okay, 1/6. So the answer of this integration is 1/6. So which means the probability that x plus y falls below this x plus y falls below this 2, this threshold 2 is 1/6. Okay. Okay, let me do one more example before the next hour. Okay. Example 2. Okay. Okay. So in this case, let us again draw the rectangle, and suppose this is from x is from 0 to 1, and y is from let's say 2 to 3. So my picture is not at all up to scale. This is 2, this is 3. Okay. And suppose the joint PDF is given by the joint PDF is given by f xy xy which is 2 over 5 times e minus 1 y e to the power x, and when x is between 0 and 1. And when y is between 2 to 3. Okay. So obviously this is not a uniform distribution. This is something else. So in 3D picture, actually what happens, the picture of a PDF is going to be something like this. So if I try to draw this in 3 dimension, so the domain that 0, 1, 2, 3 looks like this. Okay, and the function that you wrote there, that I wrote there, the joint PDF, is a picture above this domain, which is some kind of function. I don't know the picture. Okay. Okay, so this is the picture for this fxy, the joint PDF. Okay. If I draw the same picture here in the uniform case, okay, here I have not drawn that picture, but if I try to draw the PDF picture of the PDF, this is going to look like something like this. So you have this domain, which is ABCD, and on top of that domain you have the flat PDF. Excuse me. Okay. So this because this function was flat, so the function the PDF that you have here is flat for the whole region, for the whole rectangular region. Like if you look at the one-dimensional examples here, so we gave example about different type of distributions like chi-square, normal distribution, exponential distribution. Each of these have a picture. So this uniform distribution is a flat picture, but if you have so if this uniform distribution had a flat picture, if you have non-uniform case, if you have a different probability density function, you have different pictures. So in one-dimensional case, the picture is actually in 2 dimensions. So in 2-dimensional case, the picture is actually in 3 dimensions. The graph is actually going to be in 3 dimensions, and this is what I am saying here. Okay. So if the joint probability density function is like this, which means it is not a uniform distribution. And still we can talk about many different things like the marginal PDFs and etc. Of X and Y are given by again the same logic here. So for the marginal PDF of X, you do f x x, that is the integration of the joint PDF with respect to the other variable, which is f x y x y dy. Okay, so this is going to be integration. Integration of y is from running from actually 2 to 3. Excuse me. Y is running from 2 to 3, and the joint PDF is given by 1 over 5 times e minus 1 and y e to the power x. So 5 times e minus 1 y to the power x.
Extension box వాళ్ళంతా అందుకేం పనిలేదు
Okay, so y e to the power x dx dy. And if you do this integration, so if you complete this integration, this is going to be y is going to be y square over 2, and so it is 9 square, sorry, 9 minus 4, which is 5 over 2. Sorry, actually I made a mistake here. So this was 2 over 5, not 1 over 5, I guess. Let me see if it was, yeah, it was 2 over 5. Okay. And after the integration, this will become 1 over e minus 1 e to the power x. E to the power x, and this is valid for. So how do you find the domain of this marginal? You take the projection of the domain onto x-axis. So if you take the projection of the domain onto x-axis, you see that x is between 0 and 1. So the range of the domain is between going to be 0 less than equal to x less than equal to 1. And similarly, you can figure out the marginal PDF of y. So by integrating with respect to x. Okay. So f y is going to be 2 over 5. If you do the integration with respect to x, it's going to be 2 over 5 y, and for y between 2 to 3. Okay, so let's take a 5 minutes break now, and we'll be back at 10:05. All right.
Sir, have you given assignment?
No, actually, the survey is at the end of the second session.
Okay, sir.
Yeah. Okay, so let us begin again. Okay, let's start with another example. Example 3. Consider the following joint PDF. Determine whether the random variables are independent or not. Okay, the joint PDF that we are given is f x y fxy x y is equal to cx c is some constant e to the power a negative y, excuse me, e to the power negative y when y is between 0 to infinity and x is less than y and bigger than 0. Okay, so if you draw the picture of this domain y between 0 to infinity and x from 0 to y, it looks like this. So this is my x-axis, that's my y-axis. Okay, so x is equal to y is this line, and it says that for any given y, so you give for any given y, x is between 0 to y. So horizontal disbursement of x, so x moves horizontally and y moves vertically. So and this line is x is equal to y. For any given y, x goes from 0 to y. So it's like that. Okay, so this is the domain. As you know that this domain can equivalently be written as, I also talked about that in the discrete case, sometimes that is useful, can equivalently be written as, so if I do x first, so it's going to be 0 less than x less than infinity, 0 less than x less than infinity, and y is in between 0 to x. No, hold on. So y is actually from x to infinity. So other way around is that if I take any x, right? So x is from 0 to infinity for any particular x, y is running from this diagonal line up to infinity, and this diagonal line is y is equal to x to infinity. That's what I wrote here. So there are two ways to write this. In fact, there is a third way to write this, and many times it is written in that way also. The third way to write this domain is 0. Excuse me. Is 0 less than x less than y less than infinity. Less than y less than infinity. Okay. Anyway, so that was not the point of the problem. The point of the problem was to determine whether the random variables are independent or not. So first of all, let us figure out what this C is. Okay. And how do you figure out this C? We have seen an example in the one-dimensional case. There is no difference there. So the integration of the whole joint PDF must be equal to 1, which would imply that 1 is equal to integration of this joint PDF, which is C times x times e to the power negative y d let's say dx dy okay. The limits of x is from 0 to y from the given description. Bounds of x is from 0 to y, and bounds of y are from 0 to infinity. Okay, so if I do this integration, first of all, this is going to be c. So dx is x square over 2. If you plug in the y, it's going to be y over y square over 2. So it's going to be c over 2 integration 0 to infinity integration 0 to infinity y square over 2. So 2 is outside. Y square e to the power negative y y square e to the power negative y dy. Okay, and this integration is simply gamma 3. So this is c over 2, and that integration 0 to infinity y square e to the power negative y is gamma 3. Okay, so why is that? Let's go back to the previous day's lecture. It was written somewhere. Okay, so here it is. The definition of the gamma function was gamma n. Okay, so gamma n is integration 0 to infinity e to the power negative x to the power n minus 1 dx. So if I have x to the power square, like if I have x square, then this is going to be 3 minus 1. That is going to be gamma 3. That's exactly what I have here. And so this is, I have e to the power negative y square, which is y to the power 3 minus 1. That's why it's gamma 3. And value of gamma 3 is 2 factorial, which is simply 2. So this is going to be c over 2 times 2. Okay, because the value of gamma 3 is 2 factorial. That again from the previous day's lecture. Okay. All right. So this would imply that c is equal to 1. So this implies that c is equal to 1. Okay, so the actual PDF is actual joint PDF is fxy xy fxy xy which is c is 1, so it's going to be x e to the power negative y e to the power negative y, and when y is between that xy is in the specified range, so which is when 0 less than x less than y less than infinity. Okay. Anyway, now if you calculate the marginals, you would say that the marginal of x, so which is fxx, that was going to be given by integrating the joint PDF with respect to y. So joint PDF is x e to the power negative y dy, and range of y is from x to infinity. So once you finish the integration with respect to y, x is held constant. This is going to be simply x e to the power negative x. And what is the domain of x? The domain of x is going to be shadow of the whole domain. So if you take the projection of this whole domain onto x-axis, it's going to be 0 to infinity. Okay. So domain of x is from 0 to infinity. Okay. And similarly, if you do the marginal of y, it is going to be integration with respect to x, and that is going to be, so marginal of y, if y that is equal to integration of the same thing, x e to the power negative y dx, and range of x is from 0 to y, uh, 0 to y. So this is going to be y square over 2, y square over 2 e to the power negative y, and y is from 0 to infinity. Okay, now if you do this quick notice that if you take the product of these marginals, you see that you are not going to get we're not going to get this joint distribution. Okay, see clearly that if I take the product of the marginals, I don't get the joint PDF. So the final verdict is that the random variables x and y are not independent. Okay. Okay, along the same line, I would like to mention a couple of things, which is that notice that the marginal PDF of x is always a function of x. Similarly, the marginal PDF of y is also always y only. Okay, because once you integrate out the other random variable, that is not going to come into the picture, so you only get x or y. Okay. Other thing that I would like to mention here is that how do you quickly check? So quick check. So if joint PDF can be written. Actually, let me write this down. If a joint PDF is a product of functions of x and y, the domain of x and y are independent of each other, and the domain of x and y are independent of each other, then the underlying random variable random variables x and y are independent. So what do I mean here? If I look at this joint PDF that in the last example that I gave, so this joint PDF here, this joint PDF here was actually function of was actually product of functions of x and y. So for example, this joint PDF can be written as fx is equal to x times fy is equal to e to the power negative y. So you take a function fx is equal to x and fy is equal to e to the power negative y. So this is a product of independent function of x and y. So there was a possibility that x and y could be independent. The only problem was that the domain of x and y are interdependent of each other. So y is from 0 to infinity, but domain of x depends on y. So because of that, the whole thing is not the x and y are not independent. Okay. However, if you have a situation, say something like this, so my pen is not working properly. I don't know if I can write this. If I have this following situation, say we have a PDF which looks like say e to the power negative x, e to the power negative x minus y square. Okay, and suppose x and y are from 0 to infinity. Okay, so x is from 0 to infinity, and also y is from 0 to infinity. Okay, they do not depend on each other. You see that this PDF can be written as, there is a constant, some normalizing constant there. So you see that this PDF can be written as a function of x itself, which is e to the power negative x, and function of y itself, which is e to the power negative y square. Okay, so this PDF, this joint PDF can be written as function of x, function of y, and as well as the domain of x and y are not depending on each other. So in this case, x and y would be independent. Okay. Anyway, okay. So what is the next example that I was going to do? Okay, example 4. Let x follows exponential random variable with parameter lambda 1, and y follows exponential lambda 2. So you want to do a few things, okay, and independently. So independently, first thing that I would like to write is the find the joint PDF of x and y, and number B, find the find probability of x less than y. Number C, find the CDF of x and y. CDF actually, CDF of x and CDF of y. And last one, find the distribution minimum of x and y. Okay, so let's begin one by one. First one is the joint PDF. Since x and y are independent, x and y are independent, joint PDF of xy, joint PDF of xy will be the product of PDFs of x and y. Okay. So what is the product of, what is the PDF of x and y? The so fxy xy, the joint PDF, okay. So this is going to be lambda 1 e to the power negative lambda 1 x. So this is the PDF of x times lambda 2 e to the power negative lambda 2x. This is the PDF of y. Okay, and x bigger than 0, y bigger than 0. Okay, so where am I getting this? From the previous test lecture actually. The PDF of exponential distribution was given by this. So if it is following exponential lambda, the PDF is lambda times e to the power negative lambda x. Okay, so I have two exponential distribution x and y. One is lambda 1, other one is lambda 2. So I take the product of the PDFs because they are independent. So that answers the first part. Second part is find probability x less than y. So if I draw the picture of the domain of x and y, so x bigger than 0, y bigger than 0, that is this whole domain. Okay, and what we want to find? We want to find x less than y. So let us draw the line x is equal to y. So this is the line x equal to y, and x less than y is going to be this part, where x less than y. So essentially we need to integrate the joint PDF in that red color region. Okay, so integration of joint PDF in that region to find probability x less than y. So probability of x less than y is going to be integration of the joint PDF, which is lambda 1, lambda 2, e to the power negative lambda 1 x lambda 2 y. So e to the power negative lambda 1 x lambda 2 y e to the power negative lambda 1 x e to the power negative lambda 2 y and then let's do dy dx. Okay, so dy dx, if I do dy dx, the range of y is going to be, for any fixed x, range of y is from this line, which is x is equal to y, up to infinity. So range of y is from x to infinity. The range of y is going to be from x to infinity. So I'm writing in uppercase, although I am supposed to write in lowercase because my pen is not responding nicely. So I'm writing in uppercase. And range of x is going to be from 0 to infinity. If you evaluate this integration, so you are simply going to get the first step, after the first step, 0 to infinity. And then so after dy, this lambda 2 will go away, you get lambda 1 e to the power negative lambda 1 x e to the power negative lambda 2x okay, so this is a very simple integration. And dx. Okay, so once you finish this integration, you are going to get lambda 1 divided by lambda 1 plus lambda 2. Okay, so this is the probability that x less than y. So if you notice the pattern, x was following lambda 1 exponential of lambda 1, y was following exponential of lambda 2, and x less than y is lambda 1 over the whole sum. Okay, x less than y is probability x less than y is lambda 1 over the whole sum. Similarly, if you do probability of y less than x, it will be lambda 2 over the sum. Okay, what is the part C? Part C was the CDF. The CDF of x, which is f uppercase f x x that is going to be integration from 0 to x, because it's a probability that x less than or equal to x. So integration from 0 to little x, and then lambda. So let me use a different variable, lambda 1 e to the power negative lambda 1 u du. Okay, since the boundary of the integration already has x, I do not want to use x in the integration, so I'm using different variable. And once you finish this integration, this is again a very trivial integration. It's going to be 1 minus e to the power negative lambda 1 x, okay, for any x positive. Similarly, you can do the other part, if y is the same thing. Okay, for D, minimum of x and y. So let us define a new random variable z, which is minimum of x and y. First of all, let us find the CDF of z. Okay, CDF of z is if excuse me, z t that is probability that z less than equal to t, which would mean that minimum of x and y are less than equal to t. So let me write it in a different way. 1 minus probability that z bigger than t which is 1 minus probability z bigger than t means the minimum of x and y is bigger than t. So if the minimum is bigger than t, then both of x and y has to be bigger than t, which means that x bigger than t and as well as y also bigger than t. Okay. And since x and y are independent, you can write this as 1 minus probability of x bigger than t x bigger than t and times probability that y bigger than t. Okay. So now what is the probability that x bigger than t? Probability that x bigger than t can be found from the CDF of x and CDF of y. In the previous step, I found that CDF of x is CDF of x is 1 minus e to the power negative lambda x. Okay, which means fx CDF is always probability x less than equal to x, right? Therefore, the x bigger than x is going to be just 1 minus that, which is this part only. Okay, so this is the part that probability x bigger than little x. Okay, so let's plug that in back here. So if I do that here, this is going to be 1 minus. So probability x bigger than t is e to the power negative lambda 1 t, and y bigger than t is same, e to the power negative lambda 2 t, which is 1 minus e to the power negative lambda 1 plus lambda 2t. Now, if you look at the pattern, the CDF of so this looks like exponential lambda 1 plus lambda 2. So let me write down the final conclusion, then I will explain. So which is that minimum of x and y that follows exponential lambda 1 plus lambda 2. Okay, so this is the end of today's lecture, but let me explain how did I get the last step. You see that it's actually from this stage. You see that if something follows exponential lambda 1, then the CDF looks like 1 minus e to the power negative lambda 1x, and therefore if a CDF looks like this, that 1 minus e to the power negative some constant time t, then that random variable must follow exponential of that constant, okay, which is lambda 1 plus lambda 2. So minimum of 2 exponential is the exponential sum of their parameters. Okay, sorry, my pen was not working properly today, so it was kind of very annoying to me. Let me know if you have any question about the whole lecture. Suraj, your hand is raised, so do you have any question? Okay, so you can go to the assignment section. And you can take this survey, which is September 9. This is supposed to open at 10:50. It's open now. Let me see what people thought about the quiz. So, okay, so tomorrow there will be no quiz. The quiz will be shifted to Monday.